In this video, we look at more Fourier transform pairs and more about the Fourier transform properties. So first, the Fourier transform pair, delta t, frequency domain, that's 1. And if it's DC in time domain, that's 1, that's delta f. And shifted delta, that's e to the power j 2 pi f t naught, that's the only phase shift in frequency domain. And this is Fourier transform. And if we have complex exponential e to the power j 2 pi f naught t, and we only have one frequency in frequency domains, that's delta f minus f naught. And this cosine 2 pi f naught t, that's 2 delta in the magnitude and half and half. And we talked about all of this in previous videos. We just reviewed that. And sine 2 pi f naught t, that's using Euler's formulas. And pi of t rectangular, that's sinc function. And sinc t and pi of f. And if rectangular, that's sinc squared f. And sinc squared t, that's rectangular of f. E to the power minus alpha t multiplied by u of t, alpha greater than 0. The Fourier transform is 1 over alpha plus j 2 pi f. And all of it has been derived in our textbook. There are some details. Feel free to review them as well. And e to the power minus alpha absolute value t, as Fourier transform here, you're free to use it. And 1 over t as e to the power 1 over t Fourier transform minus j pi sine f. And let's talk about the Fourier transform property. We talked about this in the videos. And this is duality. We want to use it a lot. We have this x of t Fourier transform, yes, x, f. Then if I have a function of x, like a big x, the argument is t now. What's a Fourier transform? Fourier transform is x minus f. So this, the time domain function, is replaced by minus f, you will obtain the Fourier transform of big x t. Scaling property in time domain, we talk about time shift. Yeah, complex exponential multiplied by x of t and frequency shift. And you can see this pair are duality here. Let's look at this question. That's our first homework. That's 12. Question asks us to plot pi of t plus pi of minus t. So in this course, we plot a lot of waveforms. So we're going to plot. This is a pi of t. We define on that. And pi minus t, you flip the waveform over. You replace t by minus t. That's the same thing. The waveform is the same. And then you sum them up. In the same time instant, you sum them up. So this is t equals to minus half, that's 2 here. And t equals to half, that's 2 here. So that's another rectangular form. So next question, plot this triangular multiplied by rectangular. Here, remember this. When we operate on the waveforms, all the waveform has to line up with the time instant, and then we operate on the magnitude. For example, here, this is rectangular. It has some values, but pi of t equals 0. So therefore, there's no values here. That's all 0. Up to t equals minus half. When t equals minus half, this function value is 1. So it will have 1 multiply everything here. When t changing from minus a half to half. So therefore, we're going to have this here. As long as we have it here, when t less than half, that's 0. When t greater than half, that's 0. That's here. And then when t in between minus half and half, that equals this function. That's triangular function here, t plus 1 and minus t plus 1. Here, that's a special case when t equals to minus a half. It marks it halfway from here to here. That's fine. We do not have to specify that, but that because that's only one point, it's okay. As long as we have this waveform, this waveform, and this waveform, this waveform, we're fine. This is a plot, the summation of triangular waveform, n equals minus infinity to infinity, and t equal t minus 2n here. And remember three-term rules in previous videos. Please follow that. We will get that. When n equals 0, we got this rectangular. When n equals to 1, we got this rectangular. When n equals to minus 1, we got this rectangular. And when it's changing, we got more on both sides. Sine t plus sine minus t here. Again, t 0. This is sine t, right? And here is 0. And then sine 1 minus t. You need to solve this equation here. 1 minus t equals to 0. That's t equals to 1. Sine t equals to 1 when t greater than 0. So when t greater than 0, we need to solve this inequality here, less than 0. So that's t less than 1. You move the t on this side, so t less than 1. So here, this is 1 here. So t less than 1, t minus 1, that's 1. T less than 1, that's the function value is 1. And then here, this is 1 here. Okay, so that's this function. And then you sum them up. This is 0, and this is 1 here. And here, when we sum this waveform up, sum this waveform, and this waveform up. Remember, this is 1, this is 0, this is minus 1, this is 1, and this is 1, this is a minus 1. Therefore, we only have values from 0, this is 0, to 1. Others cancel out each other, so this is 1. We have, this is 0, and this is 0, and this is 1, right? And then you line them up, so the function value become 2. And this middle point is okay if you want to specify or not, that's fine. So we don't have to worry about this 1 point as long as we have the waveform drawn correctly, meaning that here, when t less than 0, that's 0. When t greater than 1, that's 0. And in this range, between 0 and 1, we have 2. But in this exactly 1 point, it does not matter in this course. Next, let's look at problem 46. 46 asks us to find Fourier transform of 1 over 1 plus t squared. What's the Fourier transform of that? This problem is to reveal the duality property of the Fourier transform. So all these homework questions are review of Fourier transform typical pairs and Fourier transform properties. We know that if xt have Fourier transform of big XF, then big xt, you replace this f with t, then what is the Fourier transform of big ext? That will be small ex. You use this function, you replace t by minus f That's a Fourier transform of this. You can see this is a duality pair. Now to find Fourier transform of this, we know from the Fourier transform pair from the early of this video that e to power minus alpha t, if I do Fourier transform of that, that's 2 alpha divided by, and then I take 4 pi squared out, 4 pi squared out here, and then alpha squared divided by 4 pi squared, that becomes that, and 2 alpha still here. Now you use the duality pair. So this is a ext, this is a exf, this is a ex of t, this is a big X of f. So now I'm going to take X, big X t. I'm going to just replace f with t, okay? And replace f by t. Exactly what we have, big X t, the argument becomes t, so replace f squared here by t squared. Okay, everything else the same. What's the Fourier transform of big X t now? According to the duality, that's it is small x minus f. So if I take Fourier transform, look, this is the arrow, that Fourier transform of big xt, that will be equals x minus f. So I'm going to find x t, replace t by minus f. So e to power minus alpha, absolute value of minus f. And minus f, you take absolute value, that's e to power minus absolute value of alpha. That's the same thing here. That's basically this. If I take a Fourier transform big xt, scaling function, and then this Fourier transform is here. That's this portion. The Fourier transform of that, that's e to power minus alpha, absolute value of f. Now I'm going to assign alpha equals to 2 pi. If I assign that, this bracket, square bracket, becomes 1 divided by 1 plus t squared. Okay? And this constant here, this constant with alpha equals to 2 pi, and this constant equals to 1 over pi. 2 alpha divided by 4 pi squared with alpha equals to 2 pi. 2 pi, this equals to 1 over pi, right? And then you move this 1 over pi, this pi, to this side here, and that's Fourier transform of 1 over 1 plus t squared.